All right. So it's supposedly recording the session.
There was a
I
pop-up
guess,
saying it's being recorded, so
yeah. Yeah, okay. So let's hope for the best. Yeah, as best I can tell, it is simply that that WebEx is down. It just stopped working. So whatever. Um, wait a couple of minutes. I mean, I can tell you something since what we're talking about right before we run into the technical problem is you were asking, once you start sending garbage together with good information, like how can you distinguish, right? We're talking
yes, it's about
about
how
it's
do we
about
guarantee that it's not tampered with?
and the one answer to that is that you are encoding information, let's say a number, as a point on an elliptic curve. So you have an agreement. There has to be a protocol for how you embed information into a point on an elliptic curve. So let me try to explain what I mean by that. Is that that let's just say that the x coordinates of points on your elliptic curves consist of, what do I know, 100 bits, right? So your prime p is like more than 100, right? But you only want to send 90 bit information at a time. So what you do is you take a 90-bit message that you want to send, and you pad the last 10 bits randomly until you find one that works. That gives you 1,024, right? 10 bits of freedom. So you have 1,024 tries, each of which has a 50% chance of working. So it will work at some point. Does that make sense? But you have this agreement from the get-go that the last 10 bits of that message are garbage. So one meaningful message could be encoded in many different ways, depending on what garbage you add to it, in such a way that you get a point on the elliptic curve. But the protocol for encoding specifies how much of that is garbage and what you should discard when you're trying to recover the message. Does that make sense?
Sure, so it's always going to say you have 10 bits of garbage and discard this no matter what, and then you can compare what's left with some way of verification. Is that what
Correct.
you're
What
saying?
is left
Okay.
is, yes.
Okay, that makes sense.
And that is called probabilistic encoding. So technically speaking, there is a very small chance that your attempt may fail, in which case the message cannot be transmitted using that encoding. But in practice, that is not likely to happen. And there has to be an agreement as to how doing the encoding and what part is being discarded in recovering the message. There may be multiple encodings that are valid for one given message. In practice, about half of the possible attempts at encoding will be successful. So does that make sense?
It does.
All right. Yeah. So all right. So let's move on. And did I see Reese at some point? Is he there?
Yeah, I'm here.
Michael Reese. Okay. So I guess we lost John. Well, I'm sorry. I'm recording this, by the way, Reese. You probably can tell. So let's. What I was telling Michael is about how to encode a number as a point in an elliptic curve. You try to embed it in the x coordinate, but you give yourself a few garbage bits that you're gonna discard in such a way to try to find an x coordinate that will actually be the x coordinate of a point on the curve. But you have to agree beforehand as to what are the bits that are going to be considered garbage and therefore need to be discarded at the end. So, but anyway. But anyway, so should we move on to the last thing? It's about signatures. So basically, what is the analog of ElGamal signatures on elliptic curves? That good?
Yeah.
All right. So again, the setting is very similar to the way we've done this working in ZModN. So again, the public setup is exactly the same one. By the way, because this is, I think, the ElGamal standard digital signatures. Or so in this case, the standard is pretty strict. It's basically like the digital signature algorithm, but for elliptic curves. It is still analog to ElGamal. It is still similar based on the difficulty of discrete logs, but the parameters are a little bit stricter. So for instance, just as before, you have an elliptic curve E over FP, but in this case, the protocol indicates that the second part of the information is a point G. You can call it whatever you want. I guess G is good because P is prime, G is a point. But you simply specify that the order of that point is going to be equal to a large prime. So you discard any small prime factors you may have until you just have, a point of large prime order. So this already means that the number of points of the elliptic curve over FP has to have a divisor that is a large prime, so that it has a cyclic subgroup of that order, right? So anyway, so this is stricter in that you really want the order to be a prime. This could be done equally well if the order is not a large prime, but in order to have a standard, you just set that to be a prime. So there's two primes here, right? P is the coordinates of the elliptic curve are modulo P, and the order of points is modulo Q. Okay? And now there's going to be a little bit of a funny thing here between doing arithmetic modulo P and also modulo Q at the same time. So anyway, remember here the setup for a signature is that you have Samantha as the signer. She wants to provide a signature on a document, and Victor is the verifier. He needs to have Samantha's verification key to verify that the signature accompanying the document is valid, right? So the secret signee of Samantha is an element less than Q. So it's an integer modulo Q, right? So let's just call that little s. So that's the secret, the signing key. And not surprisingly, the verification key, which is public, this capital V because it actually represents a point on the curve. So I'm trying to use capitals for points on the curve, lowercase for numbers. So when you exponentiate the point G using the exponent S, the secret signing key is, you get the exponentiated version of S is V, and that is public, right? So that's the verification key that Victor is going to use to verify. Now, the documents that you're gonna sign are less than Q. So the signature here is you're actually signing an integer less than Q. So that's the document D. So you're genuinely signing integers. And again, in order to do the signature, Sam as a signer, the first part of this is choosing a random integer less than Q, which is actually going to be used as an exponent. The first thing we're going to do with this random exponent E, not surprisingly, is exponentiated. So you do E times G. But that's not the signature itself. So you just compute E times G, right? The first part of the signature is the X coordinate of this point E times G. You don't actually need the Y coordinate. So again, because this is a standard, you want to make it as efficient as possible, and it is easier to transmit numbers than it is to transmit points on an elliptic curve, and you actually don't care or need the Y coordinate. So you only do the X coordinate of E times G, but there's a twist. There is something, you see this exclamation mark here? Let me explain this. There's something funny going on here. So when you compute E times G, you're finding a point on an elliptic curve, correct? And that means that E times G, the X coordinate of E times G is something that lives in the field with P elements, right? Now, in all likelihood, Q is a large prime less than P. It could be roughly as large as P, but you can think of Q as a large prime, but probably less than P. So what you do here is that you compute the X and Y coordinates of the point E times G, and you compute them as integers in the range from 0 to P minus 1. And then you reduce that X coordinate modulo Q. And the point is that this is actually, from an algebraic point of view, what this exclamation mark here is trying to tell you is that what is happening here is not a homomorphic process. Arithmetic modulo P and modulo Q, when P and Q are different primes, are usually like not really algebraically compatible with each other. So the fact that you're doing the X coordinate here and arbitrarily identifying with a number between 0 and P minus 1, right? You could identify it with another integer, which is a modulo P, but that would change S1. So there has to be this agreement that you really are computing the X coordinate of EG, but in the range from 0 to P minus 1, and then you reduce that number modulo Q. That is a non-homomorphic algebraic transformation. It's a valid function and it's perfectly well defined, but it's non-homomorphic. So there's a little bit to be aware in that. And the second part of the signature is done purely with arithmetic modulo Q. That's really weird. So the second part of the signature is homomorphic in a sense. It only involves arithmetic modulo Q. Let's look at this, right? So D was a document modulo Q to begin. That's what we're signing. S came to be as a signing key modulo Q. S1, we just made it be born as an element modulo Q. So this is arithmetic modulo Q, D plus SS1, and then you divide by E, which is also an element modulo Q, which was used as an exponent, so naturally lives in FQ. So the first part of this calculation involves arithmetic modulo P and modulo Q in some weird way, but the second part of this calculation, of the second part of the signature, is purely using arithmetic modulo Q. All right, I hope that I gave some idea of why this exclamation mark here indicates that something that is not very natural from an algebraic point of view is happening. For verification, right? So for verification, what you do is really similar to what you did in ElGamal modulo n. You do the first part of the calculation is getting this V1, which is obtained with arithmetic modulo Q as D over S2. And the second part is V2, which is S1 over S2. And the test is the test whether the X coordinate of V1 G1 plus V2 times the verification V is congruent to S1 modulo Q. And this is, again, very similar to the way this was done in ElGamal. Let me write. So, yeah, I didn't write in detail the proof that this is a test that is consistent with the creation of the signature. But the thing is that to realize is that you only do the congruence modulo Q at the very end, whereas everything before that happens doing the exponents times points on the elliptic curve. So the exponents leave modulo Q, the points on the elliptic curve live modulo P. So this is arithmetic modulo P. And at the very end, you reduce this modulo Q, right? To see if it's the same as S1. So anyway. And just as an example, anyway, but before that, I mean, is there a question about this? So I'm just gonna run through this calculation. So you see that I do exactly what I said I'm doing here. When you do it with numbers, it looks like nothing fishy is happening, but if you pay attention, you are choosing representatives modulo p, and that choice matters. But let's go, right? So again, as before, my prime 3851 and the elliptic curve y squared equals x cubed plus x minus 9 over fp, where p is that 1000. And this point G, now this is a point that has prime order 379. If you remember, this elliptic curve has 3,790 points. So there's a point P, which was a point like what, 2, 1, that has order equal to 307,090. But from that, when you raise that point P to the 10th power, so this G is 10 times P, then you get a point that has prime order Q equals to 379. All right? So I'm gonna choose my favorite signing key for Samantha is 314, correct? This is 314 modulo Q, really. So it's less than 379. And the verification key is obtained multiplying 314 by G. And when you do that modulo P, you get, you get 1200 modulo P. You just get that. Let's say that I want to send the document 271, again, the first 3 digits of E. And my random E is 123. Remember, again, this random number is less than Q because it's going to be used as an exponent, right? So when I do E times G, I get this, right? And this is going to lead, the X coordinate here is going to lead to S1, but, so this is 271. I had to reduce that modulo Q to get 376. And for that reason, it really matters that here I am choosing representatives for X coordinate. This is a point defined modulo P, and I'm choosing a representative for this coordinate that is less than P, right? Where P was 3851. So I'm using the coordinate that is less than P. And then I reduce that modulo Q, and that is the first piece of the signature. And the second piece of the signature is D plus, 271 plus 314 times 376, and we divide by 123, all of this done in Z mod Q, and you get 315, right? And for the verification, you do D divided by S2 and S1 divided by S2. So you do the corresponding arithmetic. All of this only involves arithmetic modulo Q. So V1 and V2 are integers modulo Q. And what I'm going to do with them is use them as coefficients of the points G and capital V, right? Which makes sense because V1 and V2 are things modulo Q. And when you do that, so 357 times G plus 231 times capital V, this 1200 point, you get this X and Y coordinates modulo P. But in order to verify the signature, you take the X coordinate here, and now you reduce it modulo Q. When you do that, you do get the same 376, which was S1. So there's this very last step of doing something modulo Q. And in fact, the only reason you're doing this modulo Q is so that, the secret signing keys only have a strength equal to Q. So you don't want to give a false sense of security by pretending that your key is something that gives you basically modulo P security. In reality, it's only a signature that somehow buys you certainty modulo Q. But other than that, that's pretty much it. I believe that is the last slide that I have. So checks out. And any questions about this? It is really analog to what we did for ElGamal previously, modulo N.
So I was just going to ask, could you go back in the previous slide and talk about what specifically was the weirdness that was going on? Because I wasn't 100% sure what you were.
So the thing is, right? So it's okay. So I'm here is actually is the fact that there is a morphic part of this, and that is mostly because it is a standard. So here to have of two things where each of the things is defined modulo q, then to have something modulo p and something modulo q. I mean, so whatever. What is weird here, everything up to this point is fine and consistent. That is that the secret is modulo q because the point of the secret is to be used as an exponent of a point g order q, correct? So that is the correct way to use S. It is correct to think of S as something modulo Q. Your documents, the documents are also going to be something modulo Q, and the random element is going to be modulo Q, and what that is used for is as an exponent, and the correct thing is to use an exponent, you know, that is defined modulo Q. But at this point, in computing S1, the first part of the signature, you could really just take S1 to be the x-coordinate of EG. The x-coordinate of EG naturally is an element modulo P, right? That is the key thing to realize, that this x-coordinate of EG is naturally an element of FP, just because this is a point on an elliptic curve over FP. So this is a number modulo P, correct? Right? And you're forcing an element modulo P into an element modulo Q in an arbitrary, sort of relatively arbitrary way, right? If I ask you what is the meaning, let's just say, you know, the number 7 modulo 11 is how much modulo 3. Does that make sense?
Right, so they're just putting 7 and just taking 7
Yeah.
uncritically and putting it in Q.
Yeah. It doesn't make sense to ask the class 7 modulo 11 is what class modulo 3. It makes no sense. That question has no algebraic sense. However, if I identify the class 7 modulo 11 with simply the number 7, then it makes sense to ask what is 7 modulo 3. That's 1, right? However, that is non-homomorphic. 7 modulo 11 is the same as minus 4 modulo 11, correct? And if I do minus 4 modulo 3, all of a sudden I have 2 modulo 3 instead of 1 modulo 3 as I had before. So it is not a homomorphic identification. However, it is uniquely defined. And in doing so, you transform something that was modulo P to something that is modulo Q, and now S1 and S2 are things modulo Q, and everything else works modulo Q. And in doing the verification, you do arithmetic on the elliptic curve, which works at level the modulo P. But at the very end, that coordinate has to be compared with S1 only modulo Q in the same weird way that we identify the x-coordinate of this modulo Q, right? So the x-coordinate of this point and the x-coordinate of EG need not be the same, but they are the same modulo Q. So that's just the way it is. It is a non-homomorphic step of this protocol in order to be working modulo Q. And you see, this is actually necessary to do this because this S1, which we just forced into something modulo Q, is used in computing S2, and this only makes sense if literally S1 is something modulo Q. So it is essential to do this identification to begin. But so that's the weird. I don't know whether that helps or not, but it's just that you are doing a weird thing of identifying a residue class modulo a prime with a residue class modulo a different prime, which cannot be done in the two primes are different, that doesn't make sense. In fact, by the Chinese remainder theorem, if you have the class of A modulo P can be identified with any of the classes modulo Q.
Right now, I understand now. Yeah, that does seem odd. Is there a so uh, is there a homomorphic way you could do this sort of step, but they chose not to?
Not obviously, no. Not obviously, not that I can see, not in any kind of obvious fashion. Yeah. In fact, the same is true with ElGamal doing it in modulo N. There was also this weird thing where you're doing modulo P and then modulo P minus 1. So this was also present there. So and the answer is no, it's not obvious. It's not obvious how to do this because of the way let me put it sort of intuitively. You're doing this masking, right? You're doing some kind of masking additively, correct? Here of your document, right? You're masking your document using additive. So if you're exploiting the arithmetic of points on the elliptic curve, that takes value modulo P. That happens modulo P. Whereas if you're using the secrets naturally are defined modulo Q. So if somehow you have to be able to verify a signature that involves these two ingredients, right? The random ingredient that is sort of used here as part of the signature, somehow you are doing addition and multiplication at the same time. And there is just no nice way of doing this when you are simultaneously looking at things that happen with one prime and with another one, right? The primes P and Q here are both involved in this. So there's no natural way of these S1 and S2 have to be combined in some way. They can't be independent from each other, right? So the same E that appears here in S1 appears in S2. That is essential. So the same thing has to appear in both S1 and S2. But on the one hand, that E is being used to do something modulo P, correct? Which is arithmetic on G. And also, as it literally is, which is E is something modulo P, Q. So the answer, the short answer to your question is no, there's no obvious way in which you could do this without some kind of like artificial identification. Not, at least, not really. Not really. So this may look a little bit contrived. The signatures for ElGamal and for DSA and for elliptic-curve DSA, they all seem a little bit contrived, but there is this where you are kind of working to two different moduli. The same number you're using when you're doing arithmetic, two different moduli somehow. It's just the way it is. But by all means, I mean, you can invent your own signature scheme or something, right? But it's just not obvious how to do it without being something dissonant like this, some arbitrary identification. I certainly don't know.
All right, thank you.
Right, fellows. So, yeah, right. I'm sorry about the interruption and whatever. If there's any quick questions or something, I have a department meeting and starting at 4, but I mean, I can certainly answer your questions in the next couple of minutes if you have any. And I'm sorry about the WebEx, but it's just what it is. As best I can tell, it was broken today, and about that. Reese or Michael?
I actually had a quick question on the notation on the homework.
Mm-hmm.
So on 6.10, it says,
okay. Let me 6.10. The homework problem 6.10. Okay. Yeah, I'm looking at it.
So
Uh-huh.
it says 1p2 be a basis for M. I
E
was con-
parenthesis square brackets M. This is defined earlier in the section. So,
I looked and
so
didn't
E
see it.
bracket M,
Yeah.
this is the M torsion of a group, right? Is the group of an elliptic curve.
Yeah.
So E bracket M is the set of all points P on the curve such that M times P equals the identity. And actually this is defined on page 3, beginning of section 681.
Oh, okay.
I'm sorry. I guess technically that's, but all you need is the definition. Actually, you don't actually, you know, any of the theorem of bilinear pairs on elliptic curves for that. It's a notation that maybe you never saw in your algebra class, but it is pretty standard. So G parentheses M is the M torsion points on the group G, which is the elements X, such that X to the power M is equal to the identity.
So it's just classifying all the points that have order divisible by M, or orders that divide M.
Yes. 6.10, I think, what it says is that you actually, this is a fact about elliptic curves, is that every such point that is an M torsion point, so there's a basis for the M torsion points. There's 2 points P1 and P2, such that it's an integer linear combination of those 2 points. And so, but the question is, if you had the base for the M torsion points, you would be able to solve discrete logarithm problems. So in other words, this is another way of saying that even though this basis exists for M torsion points, finding it is quite complicated. So that's just the way it is.
Yeah, the problem makes sense now that I know that.
I mean, and it's not a difficult problem. Piece of context for the discrete logarithm problems. It's as hard to solve discrete logarithms as it is to find a basis for M torsion points.
Okay, thank you.
All right.
That was my only question.
All right. Are we set then, Michael? Going
Yes,
one.
I don't have any other questions at least yet on the homework. So.
All right, fellas. I'll try to see what happened with WebEx, whether it comes back online or whatever. But you know, now we know this is the fallback if everything goes wrong. And I'll try to make these recordings available so someone who missed whatever part of this discussion can see the whole thing. And I'm sorry about that. I apologize. But the best I can tell you was just WebEx. All right, fellows. So see you. Let's meet again on Tuesday. And you know, I see that you're already working on the next homework. So good luck with that. All right.
Sounds good. Thank you.
All right, thank you, and I'll see you
All right,
then.
fellows. Yeah. Sorry about that. Goodbye.
Bye.